Hello, this is question 6 from the Step 2 paper from 2022. In this question, you should consider only points lying in the first quadrant. That is, if x is greater than 0, y is greater than 0. The equation x squared plus y squared is 2ax defines a family of curves in the first quadrant, one curve for each positive value of a. Second family of curves in the first quadrant is defined by x squared plus y squared is 2by, where b is greater than 0. Okay. Part A, then, differentiate the equation x squared plus y squared equals 2x implicitly with respect to x. Hence, show that every curve in the first family satisfies that. Right, that should be fairly straightforward, I would have thought. Hopefully I'm not really wrong about that. So we've got x squared, so we're differentiating this implicitly with respect to x. Okay, so we've got 2x plus 2y dy dx is equal to 2a, and well, clearly we're going to want to multiply by x here in order to get an x squared and an xy and all the other things they got in the answer. So multiply by x, 2x squared plus 2xy dy dx is 2ax. 2ax is x squared plus y squared. That's our original equation. So we've got 2xy dy dx is going to be equal to x squared plus y squared minus 2x squared. So y squared minus x squared, which is exactly what they wanted. Right. Find similarly a differential equation independent of b for the second family of curves. So what's the second family? X squared plus y squared is 2by. Right, okay, that's very similar then. In fact, it's the same, but they've swapped x and y around. Okay, they've called it b rather than a, but that's kind of neither here nor there. So I could rewrite this then. Let's go with blue so I don't get mixed up, because these are going to look quite similar. Just swapping x's and y's around. So 2xy dx dy is going to be equal to x squared minus y squared. So I want a dy dx bit in all of this. So I want to divide by the 2xy, flip everything upside down and multiply. So I'm going to have x squared minus y squared times dy dx is going to be equal to 2xy. Okay, so that was fine. Just flipping those around. Part B, hence or otherwise, show that at every point with x not equal to y, where a curve in the first family meets a curve in the second family, the tangents of the two curves are perpendicular. Okay. All right, so they've taken out the x equals y bit to get rid of all of these zeros that we'd have floating around. So we need to show then, what have we got? We've got this one here and this one here. So we need to show that, so this would be i.e. that y squared minus x squared over 2xy multiplied by 2xy over y squared minus, oh no, x squared minus y squared. Let's not get that the wrong way around, is equal to minus 1. And it is. So that is fine. So which it is. Therefore, we've got the tangents are perpendicular. Right, so that's done. Oh, it hasn't done all of B. A curve in the first family meets a curve in the second family at CC, where C is greater than 0. Find the equations of the tangents of the two curves at this point. Right. Is it true that where a curve in the first family meets a curve in the second family on the line y equals x? All right, so we're now filling in the gap of that special case then. Right, so the special case where y is equal to x. So we're going to have then for, well, let's say family 1. Let's do family 1 first. So for family 1, we're going to be getting then 2, which one? So I'm going back up to this equation here. And x is equal to y is equal to c. So we've got 2c squared dy dx equals 0. Okay, so that's what we got for family 1. And then for family 2, we have got that 0 times dy dx is equal to 2c squared. Okay, so in this one we've got dy dx is equal to 0, and in this one we've got dy dx is equal to infinity. Okay, so we've got a horizontal line and a vertical line. So that means that for family 1, we are going to have the tangent is going to be, so that's a horizontal line. So we've got the line y equals c. And for family 2, we've got the line x equals c. Okay, so well, they are perpendicular. So yes, these are perpendicular when y equals x, well, in brackets equals c. Right, because they're all equal to c. Right, so that's done part B. Right, this is going along fine. This is one of the better, well, I say better, I mean, they're all quite nice questions that they have in the step papers, but this one is, at least to my taste, a bit easier than a couple of the ones we've had previously. Let's see if it continues that way in part 2, but part 1 has gone fine. Given the family of curves in the first quadrant, y equals c natural log of x, where c takes any non-zero value. Okay, fine, by solving an appropriate differential equation. The second family of curves with the property that at every point where the curve in the first family meets the curve in the second family, the tangents are perpendicular. Right, so we've got y equals c natural log x, which means we're going to have dy dx is c over x. So we want something, therefore we want curves with dy dx equals minus x over c. Right, but that c has got to be the same as this c. It's not any old constant we got thrown in here, where the c's are the same. Right, so i.e., so c is, we need that c to be y over log x, so that's going to give us our differential equation, isn't it, on all of this? So that means we've got that, well, we're dividing by c, so we're going to flip that. We're going to have y times dy dx is going to be equal to minus x natural log x. That's our differential equation that we want. Just putting this value of c into here to make sure we've got the same c. So we will get then a half y squared for the y bit, and then we're going to have to do this in parts, aren't we? So, and we want to differentiate the log x bit and integrate the other one. So we'll end up with minus x squared over 2 log x, and then minus, well, that minus will become a plus, so I'll just put the plus in, the integral of the x squared over 2 and then the 1 over x dx. Okay, let's get rid of a whole load of halves out of these, I think. So let's get rid of that and that and that, which leaves me with y squared is equal to, well, that would be an x squared over 2 by the time I finish with it all, and then take off an x squared natural log x, and then we're going to need a constant, but I'm not going to call it c because we've already used c for other things. So let's go with k. So is that all I like to do? Find, and yeah, just have to find the second family of curves, which is this. So that's okay. Right, so that went pretty well as well. What have we got for part 3? And we're going to need a new sheet on this. A family of curves in the first quadrant is defined by that equation. Show that at every point where one curve meets the second curve. Oh, so we just got one family. Okay, I will go over a new sheet on this. Let's read this again. So a family of curves in the first quadrant is defined by that. Y squared is 4k times x plus k. K takes any non-zero value. Right, show that at every point where one curve in this family meets a second curve in the family. Right, okay, that's interesting. So we've got y squared is 4k x plus k. So 2y dy dx is equal to 4k. Okay, so we have to have two curves in the same family. They both got to meet and they've got to be perpendicular. So if they're going to meet then, so we're going to have two different values of k and they're going to be intersecting. So curves meet. So this means that we're going to get that 4k1 times x plus k1 has got to be equal to 4k2 times x plus k2. So that's one thing that we need going on. And then we also need that once we solve this, we can put it into our second equation for the gradients and show that they're perpendicular. So let's get rid of those 4s. And then we've got k1x plus k1 squared is k2x plus k2 squared. So I need to get x to be the subject of all of this. So that is going to be, well, I'm going to have a k2 squared minus a k1 squared divided by a k1 minus k2. So we're going to have a k plus 1k minus, k2 plus k1 times a k2 minus k1 at the top. So we can cancel the minus 1 and leave a minus overall. So we'd have a minus k2 plus k1. Okay, so that is our x coordinate of where everything's going on. Now we're going to need the y as well because that's in this equation. So we're going to need, so y squared then is going to be, oh, actually it doesn't matter which one I put in. I was just looking at it thinking y squared because we're going to have this twice for k1 and k2, but of course they're intersecting, so you're going to get the same y coordinate. So it doesn't really matter which one I put in, does it? So I'll say 4k1 times, so that's going to be minus k2 minus k1 plus k1, so minus k2. So that is minus 4 k1 k2 is what we're getting for y squared, right? So it's putting a certain constraint on the values of k that we can have here in order to get these intersections. And then I need to stick it into this second equation then for the gradients. So I need to have that 4k1 divided by, well, actually, let's say just to go with 2. 2k1 divided by y multiplied by 2k2 divided by y has got to be equal to 1 for the tangents to be perpendicular. Okay, so we've got that 4k1 k2 divided by minus 4 k1 k2 equals minus 1. So success. Yay. Or QED might be a more conventional way of rounding that off. Right, that question just flowed through really quite nicely. It was a bit to think, there's a lot to read there, so but providing you can pick out what they're actually talking about in these families of curves, I think that one was quite a friendly question. That would have been a good one to pick, I think, out of the ones we've had so far. You know, 4 and 6 have been nice questions on this paper. Question 1 wasn't that bad either. So yeah, we've already got a good chunk of questions that we can answer from the first 6